Okay, we're going to talk about static pressure and how it relates to ventilation. Static pressure in the atmosphere is the pressure that the air, all the molecules of air within the atmosphere, stacked on top of each other, basically pressing down and causing pressure. We measure that by how much that pressure displaces water in a column. That's what a barometer is. A barometer is typically filled with water. Usually use mercury. It's much more dense, and the standard is 29.92 inches of mercury for that. I looked at our barometer here in the lab, and I found that today it was 25.3 inches of mercury. So we're at elevation. We're slightly less than what we would get at normal temperature pressure at sea level. That's to be expected. It's important to understand that pressure from the atmosphere is exerted in all directions. Okay? Similar to filling up a soccer ball or a basketball. You fill it up and it has the pressure. It presses equally in all directions, thus giving you a round ball, which is what's desired. Now when we talk about ventilation, static pressure now has a new meaning. It now means the pressure inside of the duct minus the pressure outside of the duct. Okay? So if I have here a duct and I had a fan on this side, and I were to try and get air to move into here, I'm going to need to create negative pressure inside of this duct in order for the air outside to move. It's going to move from concentrations of high pressure to concentrations of low pressure, just like osmosis and diffusion. So we want to create negative pressure to get that air moving through there. Okay? There is pressure inside this duct right now, but no air is moving. And the reason is because although we have ambient static pressure pushing this way, it's also pushing this way equally, and so it's balanced and no air is going to move. But if I do something to perturb that field, if I go in and somehow create a negative pressure by suction and create a vacuum, now there's a difference in pressure and that air will move. Not unlike what happens with water. Let's take a look at some water. Okay, we have here a tub full of water, and it's not moving right now. Okay, but I'm going to take this soap dish and I'm going to pull on that water. Okay, the soap dish representing the blades on a fan in a ventilation system. Okay, when the blades on a fan move, they're going to pull and create a vacuum of negative pressure behind them. What you're going to see is that's going to cause now water to move to fill in that vacuum. You're also going to see that that water curls inward and creates some eddies behind it as it comes in like that. That curling inward is what we call a vena contracta. The water's contracting inwards and then it's going to expand again and then eddy around, not unlike the wake of a boat on a lake. Okay, after the boat drives through, the water fills that void behind it quickly and churns up, and you get a lot of turbulence. Or in ventilation, we call that turbulence loss, because it's going to cause extra stress on the fan, loss of pressure. Okay, so watch the water as I pull and it curls in around there. Hopefully you saw that. We can do that again. Not as still that time. But as it moves, you can see that water curling in around it. And the result is the movement of the water. Okay, so back to our local exhaust ventilation, our ventilation system. When the fan blade moves, it's going to create a vacuum of negative pressure. It's going to cause a negative pressure environment inside of the duct. So our new term for static pressure, some people argue that static pressure means ambient pressure and should not be applied to ventilation. That's really an academic argument. For all intents and purposes, we're now going to refer to static pressure as the pressure inside of the duct. Okay? So the static pressure, SP, inside the duct is equal to the pressure inside the duct minus the pressure outside the duct. Okay? We're really only interested in the difference of that pressure because that's what's going to make air move. Now as you look at a ventilation system, up here we've got a fan, some duct leading up to the fan, and some duct leading away from the fan. The static pressure is going to cause this air to move, vacuum on this side. On this side, the fan's actually going to have to push it. So the static pressure is going to be positive on this side, negative on the upstream or before the fan. Looking at this diagram here and these equations, as the air moves, that is also going to create another force called velocity pressure. Okay? Velocity pressure is the same thing you feel when riding a bicycle, for example. If you ride a bicycle, say 5 miles an hour, and you're sitting straight up, you really don't feel much pressure against your body. Now, if you rode that bicycle 35 miles an hour and you were sitting straight up, you would feel a lot of pressure on your body. Okay? That is the velocity pressure pressing against your body. Okay? So as the air moves, that static pressure ambient around is going to get converted into velocity pressure. Now, if the ventilation system was perfect, if it was the ideal world, okay, and there were no friction losses at all, the total pressure, total velocity pressure you could get would be equal to the static pressure. Okay? So your static pressure and your velocity pressure would be equal because 100% of that static pressure would get converted to velocity pressure. In the real world, there's going to be friction losses. Okay? So the static pressure before the fan, okay, is equal to the velocity pressure plus the losses that occur before the fan. We've got a conservation of energy pressures going on here. So we've got to account for where all those went. So because static pressure doesn't quite equal velocity pressure due to losses, we have to add those in there. So static pressure before the fan is velocity pressure before the fan plus the losses that have occurred before the fan. Now after the fan, the static pressure is defined as the sum of the losses after the fan, because just like as the fan dragged the air across the surface of the duct coming towards the fan, and that dragging caused some friction, some losses, it also has to push it on the other side against that duct, which causes some friction and losses. Okay. So on the after side of the fan, it's going to be the sum of the losses. Now note that there's not velocity pressure in here on the back side of the fan. The reason is, if we added velocity pressure plus losses, like we did for the static pressure before the fan, we would be double counting the velocity pressure. Okay? Once the air gets moving by the fan, it keeps moving, and so the fan didn't have to make it move again. So there's only one velocity pressure, and we attribute that to before the fan. Okay? So again, static pressure before the fan is the velocity pressure before the fan plus losses before the fan. Static pressure after the fan is measured as the sum of the losses after the fan. We've already counted for velocity pressure before the fan. The total pressure of a system is now the static pressure plus the velocity pressure. Okay. As we look at the diagram here, and this appears in the textbook as well, here's all the losses, all the pressures added up here, okay, the fan. This line being 0, okay, 0 pressure, 0 inches water gauge is what we measure ventilation pressure. Okay. As the air comes into the duct, it loses some of its velocity just by having to enter into that. Similar to cars getting on a freeway, traffic happens when there's merging of cars coming onto a freeway, okay? So as the air molecules have to merge and come into this duct, there's some loss there, Okay? So there's going to be what's called the hood entry loss, and that's represented here by the green. And we can hash that in this way, right? So the green portion there represents the amount of pressure that the fan had to use up to overcome that entry, the air to get into the duct. Once the air is in the duct, we also had to convert that air to the static pressure to velocity pressure. Okay? So now the blue, right here, the blue section represents the velocity pressure. Okay? So now the air is moving, it has pressure, and that velocity pressure is the same through this duct, assuming that the duct remains the same diameter. Now if the diameter gets smaller, the air is going to have to, of course, move faster, so that velocity pressure is going to increase. But for now, we'll go with a same diameter duct, and the velocity pressure remains the same throughout that entire section because the velocity is not changing. Now the red wedge-shaped section here represents duct losses, okay? Friction against the duct that the fan has to overcome. There's none initially, but that accumulates and adds up, okay? So we're adding that pressure as it moves along the duct. The pressure accumulates until you get to the fan, and you have this total pressure that the fan blades now have to move and press against in order to get the air to move. And it's in the negative direction. And we'll measure that here briefly to show you that. Okay? So static pressure is negative on the upstream side of the fan. Downstream side of the fan now is the opposite, because now the air is being pushed by the fan. Okay? And we've got this red wedge here that represents duct losses. Everything's opposite direction now, okay? Because it's all felt at the fan. So there's some lost friction here, and it accumulates all the way back up to the fan. That's the red section. And then we also have the velocity pressure, which can be measured on this side of the fan. But remember, we're not counting that as we measure static pressure on this side of the fan. We neglect the velocity pressure. We already measured that upstream side of the fan. So the pressure is negative on this side of the fan, positive on this side of the fan. You can always tell which side is negative and positive just by looking at whether the system is sucking or blowing. Okay? If there's suction, then that's negative pressure. If there's positive blowing on against you, then that's the positive side, downstream of the fan. I've got a duct here hooked up to a fan, so we're going to take a look at this with some meters. Okay, so what we measure those pressures with typically is called a pitot tube. Okay? A pitot tube is two tubes in one. Okay, one tube goes, the air blows into this hole at the front of this tube, goes in, curves around here, and goes straight out this side. Okay, if I blow in this side, I can feel the air coming out right here. So this goes straight in and out. Okay, and we'll hook one tube up to that. This way I put the section tube that has the duct tape on it so that I can tell. Okay. There's also an outer tube surrounding this tube right there. Okay. This outer tube, the entrance is instead right here. Small holes going all the way around. All the way around. There's several holes. So the air goes in through the side there, and then down and comes out this section of the tube. I'll hook the clear tubing without the duct tape up to that one. Okay. Now, how we're going to use this, if you look at this diagram, this is our duct, and this is the fan blade right here. Okay? And it's moving the air this way. So pressure will be positive on this side, negative on this side. Okay? These drawings here represent the pitot tube. Okay? So if I hook the pitot tube up like that, with the one tube coming down I will get to measure velocity pressure. But unintentionally, I will also be measuring just the ambient pressure that's pushing in all directions, represented by P here. It's pushing in all directions in the atmosphere, including into the duct. So I will be measuring the velocity pressure of the wind, of the air moving in, plus the ambient pressure. Well, I don't care about the ambient pressure. I don't want to measure the ambient pressure. So how do I subtract that out of the value? And the answer is, you hook the tube up. This hole here represents the holes in the side of the pitot tube. Okay? And so I'm going to hook this tube up against this tube. So they're fighting against each other. In essence, we've canceled out the ambient pressure. It's pressing in here, it's also pressing in here, so it cancels itself out, and all I'm left with is the pressure of the velocity pushing against it. Which, this dark section here, shaded in, represents a column of liquid in there. So if in a U-tube manometer, something like this, okay, where we have liquid filled in this, and we have pressure pushing on one side and pushing against the other, we're going to see a difference in the column of water, or inches of water gauge, which are units. Okay? And it's going to, the velocity pressure is going to be pushing against it, causing this end to lift up for an overall negative pressure. Okay. Now, if I change things around a little bit, if now I measure the pressure coming in there, but then I do not measure the pressure from the sidewall, so in other words, I pop this tube off like that. Now I'm getting the velocity pressure against the ambient pressure, which will tell me the total pressure inside the duct. Okay. This one gave me the velocity pressure. This one's going to give me the total pressure. So velocity pressure was the velocity pressure minus the static pressure in there. Okay. Total pressure is the pressure, velocity pressure, subtracting out the ambient atmospheric pressure, that would be total pressure. Or if I go to this third section here, and I only put the tube on, notice there is no hooked section, the velocity section we're not measuring anymore. I'm only measuring the side section, and leave the other one open to atmosphere. That will give me the overall static pressure of the duct. Okay. Now, on this side of the fan, it should be negative, so you'll notice that it's sucking the column of liquid up towards it. It's negative. Okay. The total pressure, in this case 0.3 inches, equals the static pressure, which is 1 inch negative, negative 1 inch, plus the velocity pressure, in this case 0.7 inches. Okay. So negative 1 inch plus 0.7 inches gives us negative 0.3 inches. So the total pressure of the system is negative 0.3 inches. It's negative, it should be sucking that column up towards the duct, which it's doing there. Okay. So the total pressure, velocity pressure, plus the static pressure. Remembering that the static pressure is going to be negative on this side. And this box helps here. Okay. Upstream of the fan, meaning before the fan, suction side, total pressure is negative, static pressure is negative, velocity pressure is positive. Velocity pressure is always positive. On the downstream side of the fan, where it's pushing now, it's not blowing the air out, total pressure is positive because it's blowing, static pressure is positive, and of course our velocity pressure is positive. Now we'll try taking some actual measurements using this fan and this ventilation system here to show you that. Okay, here is what's called an inclined manometer. By tipping this, instead of using it like that, by tipping it on its side, we get 1 inch of water now takes up that much space it's an easier graduation to read the units rather than trying to read them vertically where each inch and tenth of an inch is really small. Now it's spread out and much easier to read. Okay, but in essence we still have our U-tube here full of liquid. We've got an opening here where we're going to attach one of the hoses to the opening here, so that'll apply a pressure, whether positive or negative, on this side. And we have an opening over here to also apply pressure, either positive or negative. Now it's important to remember that the different pressures, whether they be positive or negative. I showed you that table just a second ago. And the reason you need to know that is so that you can hook them up to the right section. We always want to hook up the negative, the suction side, the greater pressure over here, okay, so that it's not at zero yet because I haven't leveled it. There's a level bubble right there. Once I level this, the column of water will be at the zero, okay. I want it to go this way, okay, either push this way or suck this side, whichever way you want to think about it. I want the column to move this way so I can measure it. If we hooked it up backwards and it moved this way, it's a short distance for it to pop up right out of here and into the tube, into my meters and in the ventilation system, and I made a mess with all this red fluid. Okay, I've leveled the incline manometer. I've got the pitot tube hooked up. Note that the section with duct tape right here that measures the velocity pressure is hooked up right here. Okay, so it should be pushing on this side and sucking on that side. I'll go ahead and kick the fan on and we'll take a measurement. Note also that the pitot tube has to be facing the direction of the airflow for it to go straight into there. So you put it in straight. I also put it in exactly halfway at the midpoint. We took a center line measurement. If we were just measuring velocity, remember that the center line is going to be a little bit higher than the average because the air flows fastest in the middle of the duct. So you'd multiply that by 0.93, and that should give you about what the average velocity would be. Short of doing a traverse where you take measurements at all the different locations throughout it, that would be your best, most accurate. But the water column got sucked this way just a little bit past 0.3. I'm going to call it 0.312 because I used an electronic meter earlier and that's what it gave me. But this, you can basically see that it was about 0.31, and it was hard to get beyond that with this measurement. But about 0.31 is the negative was the, or sorry, positive was the velocity pressure for there. Okay, now I'm going to pop off this velocity side, so I will only be measuring from the sidewall right here, and then the other tube will just be left to ambient. That is going to give me static pressure. I've written the velocity pressure on there. Now let's find out what the static pressure is. Okay, we got about 0.48 inches of static pressure. Now, let's hook it up. To just measure total pressure. So I'm going to be using just this one. The other side over there will just be open to ambient. So this should give me the total pressure. And it should be suction, which means that I don't want it on this side, I want it on that other side. Okay. Okay, so it came to about there, which is 0.17. Which is fortunate, because if we add that up, looks like everything works out today. It doesn't always work out in labs. But our total pressure equals our static pressure, which was negative 0.48, plus the velocity pressure, which was positive 0.31. So the difference between those two is 0.17. Okay, so to recap, we just demonstrated that the static pressure is what moves air in a ventilation system. And when we're talking about ventilation, static pressure is defined as the pressure inside of the duct minus the pressure outside. That delta is going to move the air. It's going to be negative on the suction side of the fan. In our example, our static pressure was negative 0.48 inches of water gauge. Okay, we measure it in head loss as inches of water gauge, or inches that it would push or pull the water up a column. We also measured the velocity pressure, which in our case was positive 0.31. If you add negative 0.48 and a positive 0.31 together, the difference is negative 0.17. So in our system, our ventilation system, we had a total pressure that was negative 0.17, which makes sense because it is suction and it's on the upstream side of the fan. On the downstream side of the fan, total pressure, static pressure, velocity pressure will all be positive. Okay. We also kind of covered the use of the pitot tube. The velocity comes in this hole right here and out this section there. The static pressure goes in these holes in the sidewall of the pitot tube and comes out this side here. By hooking those up to a manometer, you can measure that inches of water gauge to quantify all of these for ventilation purposes. Hopefully that helps clear things up. Farley, Utah State University, their industrial hygiene program.